Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from Core Memory Podcast. Joining us is venture capitalist Peter Barrett. His framework inverts consensus thinking across AI, biology, and infrastructure. Photosynthesis represents evolutionary inefficiency requiring correction. Orbital environments provide optimal conditions for superconducting computation. And advertising-based internet economics face structural collapse from agentic systems. These are not speculative scenarios, but physical necessities, according to Barrett. Here is his technical reasoning. Peter Barrett, a venture capitalist who reverse-engineered code that brought the NSA to his door at age 19, makes a technical argument that dismantles the current AI consensus. For chemistry, artificial intelligence encounters a fundamental computational barrier. The barrier originates from quantum mechanics. AI systems require training data, but classical computers cannot simulate quantum behavior in complex materials. Without simulation capability, no training dataset exists. Barrett's conclusion, humanity operates in a material stone age, discovering substances through accident rather than intentional design. He distinguishes this from the post-quantum computing era, where the transition moves from discovery to design. The magnitude resembles waking to find a million new periodic table elements. AI alone cannot cross this threshold. This design principle applies to biological systems, producing what Barrett terms correctable evolutionary errors. Plant coloration provides his primary example. Photosynthesis occurs in green plants due to chlorophyll, a molecule selected 3 billion years ago. Barrett's efficiency analysis. Energy optimization requires black pigmentation to capture all photons. Green coloration reflects specific wavelengths, representing energy waste. His proposal, edit plant metabolism to correct this ancient accident. Agricultural productivity could double, not through expanded cultivation, but through genetic debugging of crops like corn and soy. Barrett applies identical reasoning to infrastructure, specifically data center placement, producing conclusions that appear to violate engineering economics. Space presents a hostile environment for electronics, particularly for heat dissipation in vacuum conditions. Barrett's analysis inverts this assessment. He identifies space as the optimal environment for high-performance computing, contingent on abandoning terrestrial silicon architectures. His technical solution employs Josephson junctions and superconducting logic, specifically SFQ technology. These components switch using 5 orders of magnitude less power than conventional transistors, but require cryogenic operation at approximately 4 Kelvin. Terrestrial deployment of large-scale systems at 4 Kelvin incurs prohibitive cooling costs. Orbital deployment eliminates this expense. 4 Kelvin represents ambient deep space temperature. Substituting superconductors for silicon enables construction of megawatt-class data centers that are compact, radiation-hardened, and power-efficient, converting space's thermal characteristics from liability to asset. His energy infrastructure analysis contradicts current nuclear development trends. Small modular reactors dominate contemporary nuclear innovation cycles. Barrett categorizes this as misguided. Nuclear physics exhibits economies of scale rather than miniaturization benefits. SMRs frequently worsen cost per megawatt metrics. His alternative, upgrade existing large reactor infrastructure. The US nuclear fleet contains 4 zero-year-old systems operating below potential capacity. Modernizing steam generators and control systems in these facilities could unlock gigawatts without constructing new plants, essentially manufacturing capacity from dormant assets. Barrett's labour market analysis dismisses the humanoid robotics development path pursued by companies including Tesla. The standard justification for anthropomorphic robots, factories were designed for human workers, therefore robots should replicate human form. Barrett categorises this as performance rather than engineering. His efficiency principle. Human-like appearance correlates inversely with industrial utility. Human physiology evolved for savanna environments, not factory operations. Warehouse box movement does not benefit from bipedal locomotion. Legs constitute an engineering liability. The productive revolution will deploy non-human morphologies, wheeled platforms, or multi-digit manipulators that prioritize function over aesthetic mimicry. His internet economy forecast predicts structural collapse of the attention-based commercial model. Current web architecture depends on human attention, users clicking advertisements. Barrett identifies agentic AI as the termination point for this system. Future product searches will be conducted by AI agents, not humans. AI agents do not process banner advertisements or respond to influencer marketing. They evaluate data density and logical structure. This necessitates a complete commercial reorientation. Companies must optimize for algorithmic persuasion rather than human psychology. The fundamental question transitions from capturing human attention to convincing software systems to execute purchases. Barrett's methodology exhibits a consistent pattern. He disregards socially constructed conventions and evaluates only physical constraints. Whether proposing black vegetation, orbital computing facilities, or abandoning humanoid robotics, his framework treats physics as absolute and existing business or biological norms as provisional. The critical question: if these physically optimal solutions achieve technical viability, do current economic and social structures possess the adaptability required for this transition? If you're interested in the video featured in this episode, click the link below to watch the original.